The first descriptive statistic we often run into in our chapters on descriptive statistics is the mean, the arithmetic mean or the average value across a sample of data, which we denote typically by x bar, and it's basically the sum of all the x values divided by the number of data values in the data set. The next level to which we're interested in descriptive statistics tends to be the variance of our data set. So how much does our data vary around the mean? So the formula for that is really quite simple. But here we're going to enter into an entry where I'm indicating the deviation value. A deviation is how far does the data value fall from the mean. And that's going to be a very, very important value throughout statistics. We're often in our applications looking to minimize the overall deviation in a data set. So typically we've got outliers, data points that are not at our mean, plus or minus some value. We want to know how much they tend to vary around it, because two data sets with the same mean could still have very widely different distributions in their data set as we go. By squaring the deviation being the difference between the x value and how far it is from the mean, by squaring that value, we tend to exaggerate the values that are farther from the mean, so that a data set that's very, very narrow will have a lower variance than a data set that's very, very wide, even if the means of the two data sets are the same. So we square those values as we add up the deviations that we get that exaggeration of the outliers. Notice that compared to the mean, we're dividing this value by n minus 1. That's very, very important because that indicates the degree of freedom in the data. When we calculated the mean, there were n data values and we divided by n to get our values. So we didn't know what the mean was yet. But notice that in the variance formula, we already have x bar as one of our elements in the data value. So basically the sum of the data, it has less freedom than it did up here in the mean. The example being, if I tell you that two numbers have an average of 5 and one of them is a 6, what is the other one? You know the other value has to be a 4 because that's the only way you can get an average of 5. So when I already know the mean, I have less freedom. The last data value in my data set is actually something that has to be what it is in order for that to be the mean. So when we're looking at the divisions here, we divide by n to get the mean, but we divide by n minus 1 to get our variance. We don't have quite as much freedom in the data, and that's a concept you'll see throughout statistics that confuses some people, but it's actually quite simple. What is the degree of freedom of the data? So if I'm looking at the variance of a 10-element data set and I already know the mean of the 10 elements, I really only have 9 degrees of freedom going in because that 10th value is already set, or I couldn't have known my mean in the first place. So the variance is a measure of how wide our data is, where I'm exaggerating the outliers because the farther I am from the mean, the larger that deviation, the more the squared value tends to exaggerate the value. Beyond the variance, I can start to look at not just how wide is the data set, but how symmetric is it? Is it skewed one way or the other? And the skewness of your data set is gotten by, again, further exaggerating the outliers so that the farther you are from the mean, the more you exaggerate as you go through. So this formula looks fairly complicated, but it's not as complicated as it looks because the basis of the formula is the deviation, x minus x bar, just like in the other formulas. We're cubing that value as we sum them to really exaggerate those outliers. And one of the big advantages to cubing a deviation is that the result could end up being negative or positive. The variance can only be positive because we're squaring those deviations. But here we're cubing them. So we could end up with a negative number or we could end up with a positive number. And that's exactly what we're looking for. Is the data set skewed to the left or to the right? Is it to the minus side or to the plus side? And we'll be able to know that as things come through. This formula includes S. S is the standard deviation. The standard deviation of a data set is the square root of the variance. S squared is considered the variance. So we're dividing here by S to the third, standard deviation cubed. So notice we have x bar built into the formula. We have x bar is actually built into the definition of variance as we go through in getting up to our S. So in terms of our degree of freedom, not only do we have to divide by n minus 1, but it's an element of n minus 2. In essence, as we work our way down the page here, we're giving up a certain amount of freedom by building the results of earlier results, the mean and the variance, into the formula that we're using. So the more we do that, the less freedom we have for all the data values that would be involved, which is why you see the bottom of this equation getting more complex. Once I know whether the data is skewed left or right, what I'd really like to know is how tall is it or low is it? If you imagine a bell curve, what someone would call the normal curve, that we'll talk about a lot in this class, there's a classic shape that it tends to take on. But some bell curves are narrower and taller than others, and some are flatter and wider than others. And kurtosis is a measure of how much that is. So again, if you're getting used to the pattern here, you can see how the equation works, because now we're going to take that deviation as we add it up, and we're going to raise it to the fourth power to really exaggerate the farthest outliers, so that big outliers that are far from the mean will tend to pull that curve down on average, where if most of the outliers are near the mean, the curve will tend to be very tall and near it. So a measure of kurtosis is a measure of how tall or short the basic curve is. And again, because we're again taking into account more and more of the data that brought us to this point, we're losing degrees of freedom as we go. So if you think of this, the variance was the deviation squared, the skewness is the deviation to the third power, the kurtosis is the deviation to the fourth power. It's not surprising that where we had n to the first back here on the mean, we had n minus n with n minus 1 on the variance, we end up with basically n squared. N minus 1 times n minus 2 is largely n squared. So we end up with n squared here on the bottom, and down here we end up with n cubed here on the bottom. So, n squared, n cubed, you can imagine where this would go if you went into higher and higher moments of the mean. And these are referred to as the moments of the mean. And these are the four we basically need to do descriptive statistics. The first two, most of the time, 90-95% of the time, if you know the mean and the variance of your data set, you understand what that data set looks like in terms of a distribution. If you really want to know the finer details of that, you want to know if that distribution is skewed to the left or the right of the mean. That's the skewness variable. And you want to know if it's taller or shorter than the bell curve would typically be, and that's the kurtosis. So those are the four moments of the mean that we care about. In this class, when you hear me talk about it, I'm less concerned with the equations. You can always look them up. The important element for this discussion is that we're looking at higher and higher moments of the mean, looking at that first power, second power, third power, fourth power. And the higher we raise those exponents, the more we take advantage of that variation and the deviation that we have to understand the full picture of the data set. So just by knowing these four numbers, we basically know exactly what that curve is going to look like, which is important in descriptive statistics, because if we know what a curve is going to look like, we'll be able to apply a whole bunch of rules to the probability functions under that curve to be able to make inferences or predictions about what should happen in the real world based on that data. And that's the real statistical bridge between descriptive statistics and inferential statistics.